まあ、今日は日本語でいいんじゃないかという気もするけれどいつも最近悩ましいですが、ただ時々途中から日本語喋らなそうな人が入ってきたりもするので、入ってんのかな、これ。まあ、入ってんじゃないかな。Okay, so this is the penultimate lecture. And today I will talk about the classification of interacting fermionic invertible phases in the relativistic sense, in the relativistic case, which is empirically is the same with the classification in the non-relativistic case for some strange reasons. And then that will take the whole lecture today. And in the next week, I will just present the computation of various examples. So that's the idea. Before getting there, I'd like to say one thing which is not related. I have a grandmother who is still living and who just turned 100 years old today. So this morning I emailed her. So the great thing about her is that she can use emails on her mobile phone. I promised her that I will boast to the students of today's class that I have a great, fantastic grandmother who just turned 100 years old. So she's living in Osaka and I cannot celebrate it in person. So instead, I just decided to boast about her. She lived through ups and downs of Japanese society, you know. She was born before the war. She was a young lady when the war ended, you know. She was working at the bank as a clerk, she said. And well, she told me many stories, how she met my grandfather, who unfortunately died of cancer right after I was born, just 2 months after that. So I don't remember at all of the face of my grandfather. But anyways, I just wanted to say a bit about her and congratulate her for her continued health. So that's one thing I wanted to say, and that will also be recorded. Whoever who will watch the recording will know that I have a fantastic grandmother. Anyway, so that was one thing I wanted to say before getting into the topic. So 2 weeks ago, we managed to have a classification of 3 fermionic gapped phases, which are classified by K-theory and KO theory. And last week, we turned our attention to the question of classifying interacting fermionic gapped phases. And the idea we took was to consider partition functions. ZT evaluated on a D plus 1 dimensional manifold. So you want to understand D plus 1 dimensional interacting fermionic gapped phases with some additional constraint. And if you have a general interacting system, it's very hard to imagine have in your head the most general interaction terms. So instead, we would like to study them by considering the value of the partition function on we rotated Euclidean closed spacetime. And we are mostly interested not in the absolute value part, which can be changed easily by adjusting the ground state energy, but we are mostly interested in the phase part. So let's introduce a notation at IT. So our idea is to characterize these phases in terms of this phase. So this is a number, a real number, modulo 1. So it's or in other words, if you prefer a more mathematical notation, it's R mod Z, or just U1 if you exponentiate it. So we'd like to characterize this. And what we did last week was the following. I mean, even in this formulation, having a general idea of what this function could be is a difficult problem if we don't have an experience with examples. So last week, we considered this IT of MD plus 1 in the case when T is free. So in this case, this is just a phase part of the partition function of very, very massive free fermion. So although it is not very easy, but it's still computable. It's a free theory. And mathematicians has a name for it. So this is known as the eta invariant, known as the eta invariant by mathematicians. And this was introduced by Atiyah, Patodia, Zinga in the context of the index theorem on open manifold. So the context was the following. So suppose MD plus 1 is a boundary of a higher dimensional manifold ND plus 2. In that case, what the APS index theorem says is that this IT of MD plus 1 is equal to the integral over this two-dimensional, D plus two-dimensional space over certain differential form constructed from the space-time curvature and bundle curvature, if you have U1 gauge field, for example, in the case of Maxwell field. And you also have the contribution from the index of the Dirac operator on N. But today, I'm interested only in the eta invariant modulo 1. So I should emphasize that the eta invariant itself is defined as a real number. But today, we are only interested in this exponentiated version. So we don't care about the integer part, so we can just drop it because it's an integer. So this is the formula. So we know that this relation holds in the free case. And here is a jump in the logical flow of the argument. But we make here a leap of faith in saying that any interacting phase would satisfy this relation. So this is an assumption under which we will do the analysis from now on in today's lecture. There are a few ways to motivate this assumption, but I think the biggest one, again, is that this is satisfied by the free case, and I don't have much more to say. Actually, I mean, in any case, it's not a proof or anything in any mathematical sense. Let's assume that. So in some sense, we are just making a mathematical formulation of what the classification of this thing would mean. So for today's purpose, by the classification of such an interacting gapped phase, I just mean the classification of this assignment of a phase part of the would-be partition function of that gapped system on a closed d+1 dimensional weak rotated manifold. And the fundamental constraint we impose is that if this d+1 dimensional manifold is a boundary, then it is given by an integral of a differential form. So that's the essential constraint. So this is a somewhat abstract constraint. So let's see what kind of consequence it will lead to. So as n d+2, let's consider the simple case, which is md+1, md+1. So here nd+2 is just md+1 times this open interval 0, 1. In this case, nd+2, I mean, if you take the boundary, is just 2 copies of md+1. But one has orientation reversed. So let's fix the manifold M. And for simplicity, let's keep the metric G mu nu to be the same. But let's say we are considering a system which couples the electromagnetic field. And let's say we consider 2 different gauge fields on this boundary and the other boundary, right? For definiteness, let's take d equals 2, right? So this is 3, this is 4, this is 3. That's the idea. Then what does this relation mean? So holding this direction x, so x is the coordinate of this 0, 1 segment, we can consider an ax which interpolate the gauge field A on this side and gauge field A prime on the other side. So that A0 is this, A1 is that. From this, we can construct F. in the interior, then for any t, jt should be a degree 4 polynomial constructed from f. So the only thing we can think of is just f squared. And let's put some coefficient alpha, right? Then what this means is that integral of alpha f squared on nd plus 2 is it evaluated on its boundary, but the boundary has two components. So this is at x equals 1, and this is at x equals 0. And as this is a phase part of the partition function, you have a partition function on a disconnected spacetime. So it should add up. This is it of md plus 1 minus it of md plus 1. I mean, I should have also included the dependence on a. So this is at x equals 1, and this is at x equals 0. So this is the idea. Yes, so negative sign comes from the orientation reversal. So it is defined as exponential b in the partition function. And the Euclidean partition function has a general feature that if you take the orientation reversal, then this part gets reversed. So that's a very general fact about the relativistic case. And so I'm using a few properties which is peculiar or specific to relativistic case. So the conclusion we would get today is not guaranteed to be directly applied to non-relativistic systems. But in practice, the final result is known to apply to that case too in low enough dimensions. Nobody has an explicit system which goes outside of this assumption or empirical fact that the relativistic classification and the non-relativistic classifications agree for some reasons. So at present, the theory of classification of non-relativistic interacting phases is not well established. So today, I'm just discussing the relativistic case. So, on the other hand, alpha f squared is a total derivative, right? D of alpha of AF when A is globally well defined. So this side can also be written as md plus 1 at x equals 1. So AD AF alpha minus md plus 1 at x equals 0 of alpha AF. So if you compare the right-hand side and the left-hand side, we get to the conclusion that it of md plus 1 A is essentially the Chern-Simons invariant up to a constant term. So that constant is a tricky part. So in particular, small variation of it with respect to metric or gauge field is equal to the small variation of the Chern-Simons term associated to JT or JT. If you want, you can also consider varying the metric too. So here you have G mu nu prime, and here you have G mu nu, which is continuously connected by this one parameter x, right? In that case, as JT, you can consider a second contribution, which is trace beta times trace R squared, where R is the space-time curvature. Then this part is beta times trace omega d omega plus 2/3 omega cubed. So this is the gravitational Chern-Simons. And so you have beta gravitational Chern-Simons, beta gravitational Chern-Simons. So this gives you additional contribution, beta omega d omega plus dot dot dot. So this is the gravitational Chern-Simons. So in this case, if you apply Kubo formula to this effective action, you can compute the response of this gapped phase to either external electromagnetic field or to the external metric. And by the standard argument, you can translate that into quantum Hall, electric quantum Hall conductivity or thermal Hall conductivity. So in this case, alpha is proportional to quantum Hall conductivity. And beta is also proportional to thermal quantum Hall conductivity. So that's the meaning of this JT term. So in order to get these coefficients using Kubo formula, etc., the only required information is the small variation of this. And it is enough to consider D plus 2-dimensional manifold of this particular form, which is just the same MD plus 1 times the interval. And this is enough to study the dependence of this partition function, phase part of the partition function under small variation of G or A. But here, today, we are making a far stronger assumption that this particular formula that IT of MD2 D plus 1 is given by this integral of ND to JT RF holds for arbitrary way of filling in the boundary, not just that particular case of a fixed D plus 1 dimensional manifold times an interval. We are assuming this. So far in this formulation, I haven't discussed why alpha or beta would be quantized, right? So far, we haven't imposed that condition yet. But already we see that from this assumption, JT part contains the quantum Hall coefficient in the case d equals 2, or generalizations of that in higher dimensions, if you are interested in such things. Yes. Yeah. Uh-huh. Right. Yeah, it's an assumption. So in the relativistic case, that's a good question. So I think I should explain it better. So this is a specific feature about relativistic field theory. So let me get into that. So in the relativistic case, of course, the more physical situation is to consider Lorentzian spacetime with time and some spatial direction, x1 to xd. In this case, effective action or the original action should be a real function, right? So there's no such thing as the imaginary part of the partition function. Well, that's not a. So I said something wrong. In the Lorentzian case, the path integral is an integral over the configuration of fields with exponential of is, right? So and s is real. So what's integrated is always purely phase, and the integral gives something complicated. But in any case, effective action is a real function. And now you make the Wick rotation to go to the Euclidean signature. So what you do is to set t to be it, right? So what's happening is that this minus sign is annoying. So we change this to d tau squared. But what does it do? So firstly, S contains integral over dt dx1 that d, right? So this dt becomes I d tau. So this presence of I multiplies this I inherent in the quantum mechanical path integral to produce minus S, right? So that's the Euclidean version. So so this becomes a Boltzmann wave. So this is the standard relation between the statistical mechanics and in d plus 1d and the quantum mechanics in d dimensions. But this is not the whole story, because suppose in S you have a term such as partial mu phi, partial mu phi, right? In this case, what happened was that because of this sign difference in the metric, the space component of the derivative and the time component of the derivative appeared with different signs, right? And this difference in the sign also was compensated by this change. And so this became plus. So you now have not the Lambertian, but the Laplacian in the Euclidean signature. But this remained real after the Wick rotation only because there are even numbers of t derivatives. So what would happen if you have just an odd number of t derivatives? So if you have an odd number of t derivatives, this Wick rotation produces just I without an accompanying second I. So And in relativistic case, the only possibility of having an odd number of derivatives with a Lorentz invariant way is to have the antisymmetric tensor mu1, mu2, I mean, t x1, x2, xd, contracted with partial d something, partial x1, partial xd. So this is the only possibility of having an odd number of t derivatives. And this is exactly the type of contribution like AF. So the point is that in order to have an imaginary part in this effective action, you need to have an odd number of derivatives, and which means in the relativistic case, to have this epsilon tensor, which means that this is parity odd. So in general, in the relativistic theory, a Euclidean action is not necessarily an integer, sorry, not necessarily real, but the real part is parity even, and odd part, imaginary part is parity odd. So this is a fundamental feature of a weak rotated relativistic theory. And this was why in the imaginary part, which we are talking about, or its derivative, which is nd plus 1 jt rf, could only contain f wedge f, but not ff. So this part can contain ff epsilon, but not f mu nu f mu nu. So f mu nu f mu nu is parity even, so it's a real part, and it doesn't contribute to this imaginary part. Only the ff with differential form contraction is parity odd and can contribute to the imaginary part. So that's the special situation in the relativistic case. And you now understand why I started today's lecture by saying that today I'm using lots of information from relativistic case. So this underlies the property I used. For example, in the derivation, I said that this is at x equals 1 and at equals 0, right? And I mean, it is reasonable to have this because the system is disjoint, right? And Taka-san asked me why I got the minus sign by changing the orientation, and this is because of this property, that the imaginary part is parity odd. So this is part of the condition which is called reflection positivity in various literature about statistical physics or the mathematically precise treatment of quantum field theory. So you cannot have an arbitrary function as the Euclideanized action of relativistic theory. So this S has to satisfy a condition called reflection positivity. I haven't explained the positivity part yet. So in order to talk about reflection positivity, something first must be reflection real, and then you need to exclude the case of reflection negative, and you say reflection positivity. So so if a function now satisfies the property that it's real under rotation, but imaginary under reflection flip, then it's called reflection real. And that's a slightly different property, right? Than yeah. Then, in order to have a unitary theory, you need to impose positivity. So that's one thing. You see that this is a confusing point for anybody who learned 2D CFT, for example. So suppose you have learned 2D CFT in both either Kondomat or HepTH. And I said repeatedly in the lectures we had that if you have X direction and a T direction, then you have left moving and the right moving fermions, right, which can be both real, right? So they have correlation function, but it's useful to Wick rotate T to tau and consider the complex coordinate Z, which is X plus I tau, right? And so this corresponds in the original not non-Wick rotated variable. This is just a light cone coordinate. And in terms of Z, you know that the correlation function of purely, say, left-moving fermion, which is real in the original part, to have 1 over Z minus W, right? I mean, this is a very fundamental formula, and you get immediately confused. I mean, if you have learned CFT and if you are not confused, I guess you are missing something. This is supposed to be real fermions, right? So psi's are real fermions, but if you Wick rotate to go to Euclidean theory, the basic, very basic correlation function is a complex number, right? So what's going on? What the heck is going on? So that's the question you should have asked. And what is going on is that if you Wick rotate a Lorentz invariance theory, because of these reasons, the reality condition of the partition functions and the correlation functions are not an obvious one. But it's the reality condition you have is this versions of reflection reality. So this is a statement about the exponent of the effective action. But in terms of the partition function, the statement becomes that the reflection of the coordinate, a correlation function is a reflection real if the parity flip becomes a complex conjugation. And if you flip the parity, I mean, if you say in Lorentzian coordinate, I mean, one parity transformation is sending X tau to X minus tau, right? And this will change the complex coordinate. So the flipping it becomes, changes 1 over Z minus W into 1 over bar Z minus bar W. And this is exactly what you should expect for a Wick rotated correlation function of real fields. So these are the underlying reasons why you should expect only F wedge F in the imaginary part of the Euclidean action. Thank you for the question. I was thinking of not explaining it, but but you are very good, you know. No. You are very good. That's indeed an important physics point. Yes, go ahead.
Yeah, this explanation, make me more doubtful on this discussion, right? Like, it sounds like your effective action, if you assume that that only.
Yeah, right.
If you allow our target of the preventive system is include the nominal risk one, and if so, you should think about the additional term.
I know, yes.
My expectation is just including that, you can go on the similar analysis, and then you will get the same result or not, and then maybe that's the point. So.
Right. So So conservative point of view to take here is that I'm doing a classification of relativistic interacting gapped phases. And for example, so this result I'm going to explain in the rest of today's lecture lead to a number of predictions for the classification, right? And that was taken up by serious mathematical physicists who actually prove things as a question to be shown. And Ogata-san, who uses functional analysis and operator algebras to classify these gapped phases, to prove this classification one by one. So she successfully reproduced the classification. So what Ogata-san did was to consider a non-relativistic Hamiltonian analysis of gapped phases in d plus 1 dimensions. So, or just d dimensions. So she considered d-dimensional lattice with fermions, and with her functional analytic approaches, she could consider arbitrary Hamiltonian, and she did the classification. And for d equals 1, I don't know how fast she went, but for the first few dimensions, she reproduced the relativistic classifications. But at d equals 2 or d equals 3, she found a slightly different classification. So, and I discussed with her for some time, and we realized that her classification becomes the same with the relativistic classification if you impose by hand that the system in this d dimensions have CPT symmetry. So as you know, in relativistic systems, certain discrete anti-unitary symmetry called CPT is imposed. And if you consider an arbitrary non-relativistic system, CPT symmetry is definitely not there. But that doesn't matter in the classification in low enough dimensions. But in her classification, in order to match d equals 3 case, or maybe it was d equals 2 case, I don't exactly remember, she needed to impose by hand the CPT symmetry. Yeah, so that's the situation. So what I'm going to say can be different in the non-relativistic case. So that's something you should keep in mind. Also, Ogata-san's analysis did not exactly say that there's an actual difference in the classification in the non-relativistic case and the relativistic case here, because what she did was to characterize the possible signature of, so she constructed various invariants of gapped phase, which is invariant under the continuous deformation, but she did not produce actual systems giving you non-trivial examples of those classifications. So in her analysis, at present, there seem to be cases where there are not CPT symmetry. CPT symmetry is not there in the system, just as an abstract classification goes, but she has not produced an actual Hamiltonian that belongs to that non-CPT invariant system, because her method of classification is not quite constructive. So I presume that there is such a system which does not have CPT symmetry, which is therefore fall outside of the relativistic classification in the non-relativistic case. But that's something somebody has to produce. I think that's a very interesting question to actually write down an example of that. So
let me clarify.
yes.
Means
Yeah.
some clarification is one with the reality.
That's right.
Without assuming the CPT, you will get the.
Yeah, yes, slight difference. Yes. So there's a possibility. So the correct way to say this is that she could not prove the existence of CPT in the case of non-relativistic systems, right? So it might be just that she has not just yet been able to deduce the existence of CPT, right? So that possibility has not been excluded mathematically. So that part can only be solved by constructing an example where CPT invariance just doesn't exist.
I forgot how it works, but how work is also applicable to the thing as well.
That's right. Yeah. So she found a difference in the fermionic case. Yeah. In the bosonic case, for the first up to d equals 4 something, the mathematical expectation is just you get this digraph-Witten phase. And she continued to show this fact for higher d. And yeah.
Higher dimension one is there.
That's right. That's right. Yeah. So that's the status. So please remember that what I'm telling you today is for the relativistic interacting phase, which seems to agree with the known results in non-relativistic case, as far as concrete examples go.
You expect that your treatment is like considering the non-relativistic one and considering the old possible terms, and the appearance of liquid are not full. It gives the too many terms.
Yeah. So there is another method proposed by, that will be the topic of next week, but let me just say anyway. So in the rest of today's lecture, now I will temporarily stop talking about physics and introduce you the Boldism groups. So I will talk about pure math for 30 minutes or so from now. And I will introduce Boldism groups and say that the interacting phase, relativistic interacting gapped phases can be described by Boldism. So that's what I'm going to say. And what I'm going to say next week is this. I mean, digraph-Witten phase correspond to ordinary homology, right? And the free fermionic phase we discussed last week correspond to KO something. I mean, there's always a shift by some number. We didn't discuss the case with symmetry in the free fermionic phase, but this is what it is. And in the case of Boldisms, again, we have something like this. So this is the bosonic case. This is the free fermionic case. This is the relativistic interacting fermionic case. And mathematically, they are all examples of so-called generalized cohomology theories. So also, before people came up with this very general classification, there was an intermediate phase where Gu and Wen considered the interacting fermionic phase by Hondo-Matt-Wei, and they introduced something called super cohomology, SHBG. And this also turned out to be a generalized cohomology theory. So the empirical observation around 10-ish years ago, was that for any question of classification of interacting or non-interacting invertible phases led to some generalized cohomology theories. And there's a very general argument by Kitaev saying that even in the non-relativistic case, the classification result of the gapped phase would result in some generalized homology theory. So Kitaev has a very abstract argument saying that any classification result of this class of theories should give some generalized cohomology theory. And these are just examples of that. That is why algebraic topology and the theory of generalized cohomology theory will be useful in this type of classification result. And there is an unpublished work by Kubota-san, who's a mathematical physicist, I mean, pure mathematician in Kyoto, who generalized the analysis of Ogata-san by just formulating the d-dimensional lattice system analysis using functional analysis and operator algebra, showing that the classification of non-relativistic gapped phases with fermions or without fermions gives you actually a generalized cohomology theory. I think it's okay for me to say this because he gave a talk, a number of talks about this in a number of conferences. I mean, the paper is not yet available as far as I know. So this is still true. So the answer to Taka-san's question is that in the non-relativistic case, even in the non-relativistic case, this agrees with this for low enough d. And among generalized homology theories, things like this very often happens. So two generalized homology theories agree in low enough dimensions, but start to diverge if you go to high enough dimensions. For example, what Gu and Wen proposed agree with this for the first few d, but start to diverge. And this is too simple to describe the full complexity of this. Also, this Digraph-Witten phase, which people often say as the classification result for the bosonic phase, is not quite true either. This is known to agree with the true result, which is also given by the Boldism, but not with spin structure. They start to diverge when d equals 6 or something. It doesn't matter for us because we live in 3+1 dimensions. But if you mathematically study the question, they start to differ at d equals 5 or 6. So, so this discrepancy between the relativistic and non-relativistic classification is another example of this. Yeah. So I'm going to, I think all the physics I'm going to talk will be contained in today's lecture. And the last lecture next week is just about mathematical theory of generalized cohomology theories and how to compute these groups. But the reason why that seems to be useful is due to this Kitaev's argument that for any type of classification result with a number of symmetries, you get generalized cohomology theories. Yes?
Origin, you also just classify the interacting bosonic.
That's right. Yeah. Oh, yeah. Gapped, trivially gapped systems. Yes.
Okay.
Yeah. I'm going to talk a bit about that next week. Yeah. Okay, so thank you for the questions. That's exactly the reason why I'm doing this as a lecture series. I mean, I need input. Okay, so let me introduce Boldism groups. So for this, we consider manifolds equipped with some structure. which I call S. This is very abstract, but S can be just orientation or spin structure. Or if you don't even need orientation, just smooth structure. So you can impose further conditions, various conditions on the tangent bundle. So Borodism can be defined for each. Now, let's say we have a manifold MD and another manifold MD prime, so MD prime. And suppose if you have a D plus one dimensional manifold such that it has an incoming boundary and the outgoing boundary, then we say MD and MD prime is Borodant. And this ND plus one itself has a Borodism from MD to MD prime. This is a Borodism. I don't impose any connectedness condition. So, I mean, ND plus one can even contain disconnected component like this. I mean, ND plus one can be this part and the other part. Yeah, MD can be disconnected too. And so, I mean, it can be like this. So in this case, the incoming boundary has two disconnected components. Outgoing boundary has one component. And the Borodism between them can also have disconnected parts like this. And we demand that every manifold appearing it has the same S structure. So if you want to specify or emphasize this, you can call them S Borodant, and this is S Borodism. And in particular, when MD prime is empty, I just call it 0, and we say MD is 0. This is called no Borodant. And such an N D plus 1. So this is now Borodism. So now Borodism is just MD filled with MD plus 1. And again, I emphasize that both MD and MD plus 1 is equipped with the structure S. It's fairly clear to see that this relation is an equivalence relation. So the set of equivalence classes I denote as omega S D. So this is the Borodism, S Borodism group. So you can have oriented Borodism group or spin Borodism group or unoriented Borodism group by changing the structures. And I still haven't explained why they are groups. I mean, we just considered manifolds and the equivalence relations. So we have just a set of equivalence classes. But addition is easily described. So I just define. So this is the notation for the equivalence classes. So to take the sum of two equivalence classes, we just say that it's a class of the disjoint union. Sorry, MD, right? So, I mean, because you guys asked me already questions, so I mean, the sum of equivalence classes is just taking the disjoint union. So nothing is simpler than that. And I haven't yet explained why this is a group, right? This makes it an abelian monoid. So you need to show the existence of an inverse. What's the additive inverse? So additive inverse is just MD's additive inverse is just the same manifold with the opposite orientation. In order to show this, we need to show that MD plus MD bar is 0, right? So we need to, so coming back to the definition, we just need to construct a Boldism MD plus 1, which is a Boldism from MD disjoint union with MD orientation reversal goes to empty. And this is very easy to get because we can always have this trivial Boldism by considering MD times 0, 1, right? But this is incoming boundary, this is outgoing boundary. I can move this to the incoming side by writing this. But because I moved this, this orientation is reversed. So this is MD inverse. And you don't have the outgoing boundary. So this is just a Boldism, null Boldism we wanted. So this makes omega ds into actually an abelian group. So this is a vanilla version. Let me now introduce the concept of omega ds x. Yes, go ahead. That's also a good question. When manifold is unorientable, so that happens when you consider S to be unoriented, right? So in that case, the additive inverse is just itself. You don't do anything. You don't have to do anything because you just don't introduce orientation. But this fact is still true. But this also shows that in omega d unoriented, every element has the feature that if you multiply by 2, it's 0. And indeed, I already prepared this table. And everything is Z2, right? Because, you can never have Z. That's the interesting part. So thank you for the question. Right. Cobordism category? Cobordism category is a category where objects are MDs before taking the equivalence class, and morphisms are the Boldism. Yeah. So for any category, you can introduce a corresponding group by saying that you take the equivalence classes of objects in the category. If you have a non-zero morphism, you identify them. So if you apply that construction to the Boldism category, you get the Boldism group. So the definition of this is very easy. In this case, each entry is not just MD, but with a map from MD to X. So you fix a target space X, and you consider MD and MD prime, and you always assume that a map is given to this X. And even during the Borodism process of ND plus 1, you assume that the bulk part also has a map to this X, such that the map X here restricts to both incoming boundary and outgoing boundary. So you can introduce equivalence classes of such pairs of manifold with S structure together with a map to X. And you get this. In particular, when X is a point, this group I just introduced is actually the same as this one we already introduced, because when this point is just, target space is just a point, I mean, you always have a standard map for a manifold to this single point, right? I mean, this can be trivially added, so nothing changes. So if X is point, nothing happens, and the construction goes back to the Borodism group of S manifolds I just introduced. And finally, if you consider omega ds of Bg, where Bg is the classifying space, what you do is the following. Now, in the process of the definition of the equivalence class, you consider a map to Bg, right, at every step. But Bg is a classifying space of G bundles. So instead of saying that you have a map to Bg, you can just say that you have a G bundle over it. So this is the group of Borodism classes of S manifolds with G bundles. So these are the concepts. And yeah, so here are some examples. So here, this is unoriented Borodism group. This is oriented Borodism group. This is pin minus Borodism groups, spin Borodism groups, pin plus Borodism groups. So this is a Borodism group of spin manifolds together with Z2 bundle. This is the Borodism group of spin manifolds with U1 bundle. And finally, this is something called spin C structure Borodism groups, which I might have time to explain, or I might not, but these are the results. And for reasonable x's, omega SD of Bg is always of the form Z to some power k plus some number of Z and I's, right? So there are some numbers of Z components and some number of Zn, Z2s or Z3s. And people call this part torsion part, and this part non-torsion part. Just because in the basic theory of abelian groups, if some element becomes 0 by multiplying by n, that element is called n torsion. So if 2x is 0, x is 2 torsion, etc. So this is the torsion part, and this is non-torsion part. Actually, people often say this is free part, not the non-torsion part. But this terminology is a bit confusing for us, because we are going to say free part of the interacting classification, by which I do not mean that this ZK part corresponds to, free in the sense of quantum field theory. So Z is known as often said as a free abelian group or generated by one element. It's free in that sense, but not free, not necessarily free in the sense of quantum field theories or quantum mechanical systems. So I try to not use the adjective free in this case. I try to say non-torsion. So, but anyway, this is what it is. So before getting back to physics, let's look at some examples and how to understand them. So how do I know? How do we know if a given MD is non-zero within omega d s? How do we know that? This can be done via something called Borodism invariant. So let me start with an example. So say you want to study, let's say, something with d equals 4. So you have, in d equals 4, there are a number of z here, right? Z factors. In this case, suppose you have M4, and suppose you have M4 prime, and they are, let's say they are Borodant by N5. In this case, there's a characteristic class called trace R squared, which is proportional to P1 von Triagin class. In this case, you can easily show that integral of trace R squared on this side and on the other side is the same. It's very easy to show this because if you take the difference, this is by Stokes' theorem, an integral of d of trace R squared. And because this is closed, because it's a characteristic class, this is 0. So this is 0. As easy as that. Yes. In the Borodism category, please assume everything is smooth. If you don't, so as I said in the very first lecture in last autumn, you can consider non-smooth Borodism groups, etc. They will add and subtract various things. Yeah.
This table, all the things
Yeah. So these are smooth Borodisms. Yes. So you can consider piecewise linear Borodisms and the topological Borodisms if you'd like. Yeah. But here, in any case, I'm doing this classification for the relativistic case with weak rotation, etc. So I think it's reasonable to assume smoothness. Okay, so if you have a manifold M4, and if you compute the integral of trace R squared, if suppose it's non-zero, right? Then it can never be 0. Because if it's now, then the integral here is 0. So this should be 0. So if you have a Borodism invariant, and if it's non-zero, then that manifold gives you a non-zero Boltzmann class. It's as easy as that. There's an important theorem. There's an important theorem. Non-torsion factor, these summands of omega ds are in one-to-one correspondence with these differential form characteristic classes. So in 4 dimensions, these so these can all be measured by just trace R squared, which is proportional to P1. But here you have Z2, right? Z squared. And the reason is that you have U1 bundle. If you have U1 bundle, you can also consider F squared, right? So this is called C1 squared in the algebraic topology sense. So if in these 3 cases, because of the choice of the structure of the manifolds, the only degree 4 differential form characteristic class you can write is trace R squared. Correspondingly, there's just a unique factor of Z. In this case with BU1, or in the case of spin C structure, which also has U1 bundle, you can not only write trace R squared, but also F squared. And that gives you additional choice, which is Z squared. So this makes it easy to count, obtain this K, the number of non-torsion part, number of Z summands. All you have to do is to try to write down all possible differential form valued characteristic classes coming from R and F. So for example, well, there's not much example. Let's see, this is Z2, right? So this is dimension 6. So for dimension 6, there should be just 2 differential form characteristic classes, right? So here you have R and F, and you need to construct degree 6 characteristic classes. And yes, you can write it. Easy thing is that, so I'm discussing spin BU1, 6, right? So degree 6 invariants are either trace R squared times F or F cubed, right? So that's the only thing you can create, and that gives you this Z2. So this is fairly easy to recognize. I didn't talk about these Z. These are just 1, you know. In the 0-dimensional case, you can just integrate 1 to get to 1, right? But in order, you need to remember that even a point can carry a positive orientation or a negative orientation, right? So if you have 2 points with positive orientation, you cannot connect it. But if you have a positive orientation point and a negative orientation point, you can connect it continuously and make it disappear. So this means that if you have a number of 0-dimensional points with orientation assigned +1 or -1, the only deformation invariant, Boltzmann invariant, is just the sum of all these orientation numbers, and that gives this Z. moves us onto these Z2 cases, right? So if you don't have orientation, if you have 2 points, it can be connected into nothingness. But if you have just odd number of points, you can never make it disappear. So that makes them Z2, right? So we also understand them. So we are getting better. I mean, we are understanding more and more of these entries. So let's move on to torsion parts. That's right, yes. Non-torsion part corresponds to perturbative anomalies, yes. And non-torsion part corresponds to Chern-Simons terms and the quantized Hall coefficients, etc. So these are Z-valued objects. I'm going to explain the connection soon. Yes, go ahead.
Z2 is torsion.
Yes.
Okay.
That's the torsion part. So this argument of constructing Boltzmann invariant applies to other characteristic classes too. So if you use differential form like trace R squared, the crucial input was this, right? And this gave us Boltzmann invariant. This important relation led to the fact that trace R squared integrated over M4 gives you a R-valued Boltzmann invariant. Similarly, W2, we talked about Stiefel-Whitney class last in autumn. So this is an element in H2 of MD Z2. And this satisfies the condition that the coboundary is 0. And you can just apply the same trick. So say you have M2 prime connected by N3, then you can consider the characteristic class W2 in the entirety N3, then integral of W2 over M2 minus integral of M2 W2 is by the Stokes theorem, integral of dW2 over N3. And because of this property, this is 0. Therefore, we learned that W2 integrated over M2 is a Boltzmann invariant, although now taking value in Z2. So formally, the procedure is exactly the same as the one we did with the differential form case. I mean, the only difference is that here it's standard exterior derivative, and here we are using the delta operation in the discrete valued co-cycles. And that explains, for example, this Z2. So the generator of this Z2 of unoriented case is actually RP2. RP2 is obtained by starting from S2 and taking the antipodal identification. And I don't remember if we discussed this integral of W2 over RP2 back in autumn, but this turns out to be 1. So this is non-zero. So this explains this Z2. This can also be understood. I mean, in 5 dimensions, there are characteristic classes obtained by multiplying W2 and W3. So Wn is the standard degree n Stiefel-Whitney class. And you can take the product, and this is a closed cocycle. So you can integrate this on M5. And this can either be 0 or 1. And there are manifolds for which this is actually 1. Although I don't prove it, let me mention example where this is 1. So this is known as the U manifold, which is just SU3 divided by SO3. So this is 8-dimensional, and this is 3-dimensional. So 8 minus 3 is 5, and if you evaluate this, it's actually 1. And in the analysis of our free fermionic phase, this is also the same as the space of a symmetric 3 by 3 unitary matrix U with det U equals 1. So it's a funny manifold. Yeah, this generates both Z2 in the unoriented case and the oriented case. So this is an orientable manifold. It's not such a strange manifold, right? I mean, this concept can be understood by anybody who learned a bit of linear algebra, right? You just consider 3 by 3 unitary matrices of determinant 1, and somehow you impose symmetricity, and that's 5-dimensional, and it actually generates this Z2. So that explains a lot of things, but not quite. For example, this Z2 in dimension 1 in the pin minus or spin case is a bit more difficult. So let's consider, here we are considering 1D manifold, right? 1D manifold is oriented, and then spin, say, right? So in the oriented case, the Borodism group is 0. Why is that? Well, the point is that if you have an oriented 1-dimensional closed manifolds, these are just disjoint unions of circles, and any circle can be filled in, right? Preserving orientation. So oriented Borodism group of degree 1 is 0. Why do we have Z2 here if you impose a simple spin structure? So this is because in the spin case, you can either have R sector S1 or NS sector S1. So this corresponds to a periodic spin structure. Fermion is periodic. And this is anti-periodic spin structure. And it is known, again, that if you have a circle bounding a disk, the spin structure here is automatically NS, or anti-periodic. This is counterintuitive, because you might say that this can be continuously shrunk to a point. So you would think that this is a periodic. But the point is that if you change the coordinate system from the plane to this semi-cylinder, with a hemisphere attached, you need to take, so this is W and this is Z, and the W is exponential of Z. Sorry, it's the other way around. Z is exponential. And if you do this transformation carefully, because it's fermion has a spin 1/2, you get the minus sign popping up. So the fact that the periodicity of fermion being periodic in this coordinate system means that the fermion is anti-periodic in this coordinate system. Again, this is a confusing point when you first learn relativistic fermions in CFT, but that's a fact. So this is a difference, and this Z2 measures whether the circle is in N sector or R sector. This can't be measured, detected by this cohomology class, Z2 valued cohomology class. So because the only characteristic class available is Stiefel-Whitney class. So let's try Stiefel-Whitney class. But Stiefel-Whitney class integrated means the orientation. So it is -1 if orientation is reversed. But here orientation is preserved. So this is 0. So this is not detected by the standard homology valued characteristic class. Instead, you need to use the eta invariant. So last week I said that eta invariant for the R sector circle is 1/2, and the NS sector eta invariant is 0. So they are different. And I forgot to. So recall the APS index theorem, which says eta d is n d plus 1 with some differential form plus index of d plus 1. And if we are interested in eta invariant modulo 1, we can forget about this. And furthermore, if we are in odd dimensions, here it's a bit more difficult. Good. Here we are considering one-dimensional manifold, right? So here we consider two-dimensional manifold. So in principle, there can be some differential form which can appear here. But here we are considering spin structure only. So the only thing we are available is R. And you can only construct R squared, but not trace R, because trace R is 0. So there's no such term appearing here. This means that if you have two one-dimensional manifolds, I mean M1 and M1 prime, the difference of the eta invariance is by this token N2 with this differential form. But because there's no such differential form, it's 0. And because of these reasons, eta invariant gives you a Boltzmann invariant. So if this is non-zero, it is a non-trivial class. And that's how you can detect this Z2 and similarly this Z2. And all the other Z2s can be detected, and Z16s and Z8, they are all eta invariants. So typically, I mean, all of the entries here can be detected by 3 type of objects. So we had R-valued Boltzmann. I mean, differential form characteristic classes, and Zn valued characteristic classes. And then eta invariants. And they give useful Boltzmann invariants, which can detect all of the entries I wrote here. If you go to higher dimensions, or if you consider more complicated groups, it is not true that these three are enough to distinguish all of them. In some cases, you need more complicated invariants, but in most of the cases, they suffice. Right. So these are how you can understand algorithm classes. And I wanted to come back to the classification of the interacting fermionic phases. But the time is kind of up. How should I do? But can I continue until 12:15 or something? In any case, it's a completely voluntary because it's not a good place to stop. I just want to state the final statement. So with this information, let's come back to this study of ITMD plus 1. Now, in order to talk about the theory, you need to specify space-time structure. So orientation or spin. So orientation corresponds to bosonic theories. Spin corresponds to fermionic theories. And just considering unoriented corresponds to a time reversal invariant bosonic case. And you can consider pin minus or pin plus. These corresponds to time reversal invariant fermionic with t squared being 1 and the t squared being minus 1 to the f, etc. So these are the standard changes. So now these symmetry properties are encoded in the type of structure S used in the Boltzmann analysis. And remember, this is given by n d plus 2 with jt r f. So what's the constraints we have here? So here, this should be well-defined modulo 1, right? But if you have MD, there can be multiple ND plus 2. So let's say we have two such things. So let's say we have two such things. So we should have this relation too. But this is not yet guaranteed. So we have the condition that 0 equals n plus d2 prime jt minus nd plus 2 jt. And as always, we represent this negative sign. Is plus is orientation reversal. So this makes it into this. Then this sum is just jt evaluated on this closed manifold, right? And you say that, well, integral of jt became 0. How could that be? Well, remember, this is only defined modulo 1. So this means that this mod 1 1. So this means that we need, so this means that JT is such that if it's integrated over closed n d plus 2 should always be an integer. So that's the condition on JT, and this gives the quantization condition on alpha. So this JT gives a map from omega d plus 2 to z. You see? JT, if you integrate over closed d plus 2 dimensional manifold, gives you a map from the Boldism group with dimension d plus 2 to z. It's a complicated formula. So let's do some examples. So let's, as always, take d equals 2 with s is either orientation or a spin. In that case, I say that JT is, in any case, alpha times trace of r squared. And in algebraic topology, it's conventional to use integer quantized P1, which is trace this one. So let me just use P1 instead. And we consider orientation Boldism or spin Boldism. And both are Z, right? But they are not quite the same. It's known that this is generated. One corresponds to CP2, on which P1 is integrated to 3. But the CP2 doesn't admit spin structure. And one smallest unit here is known to be given by some manifold called K3. And the integral of K3, P1 over K3 is 48. This is a math fact. And from this, a JT for oriented case needs to have this property that JT is integer nu times P over 3. In the spin case, it's instead nu times P1 over 48. You see, P1 over 48 integrated over K3 is 1, right? So it gives a map from spin Boldism group is d plus 1, 2 equals 4 to z. So this is the correct normalization for the spin case. And this is correct normalization for the oriented case in the prime. So for example, and as I explained, these corresponds to the quantized thermal Hall conductivity. And if you know some physics of that, if you have a thermal quantum Hall effect material in 2 plus 1 dimensions, if you have a boundary, you have a chiral mode C with some central charge, chiral central C. And C appears as the coefficient of P1 divided by 24. I mean, normalization is different. So this predicts that the central charge of the chiral edge mode is 8 times an integer. And in the spin case, this predicts that chiral central charge is half integer. And these match what quantum math physicists have often said. So nu equals 1 corresponds to kita F's E8 phase. That's a bosonic interacting phase with whose thermal quantum Hall coefficient corresponds to C equals 8 on the boundary.
Sorry,
Yes.
So you discussed the 4D.
4D case, yes.
You talk about what that's.
Yeah, then, no, I mean, that's the confusing part. That's the confusing part. So I'm talking about gapped phase in 3 dimensions. I'm talking about gapped phase in 3 dimensions. Yeah, 2 plus 1 dimensions, right? And this is given by the integral of JT over 3 plus 1 dimensional manifold. This is why, if you want to discuss D plus 1 dimensional gapped phase, you need to consider map from D plus 2 dimensional Bourdism groups to Z. So in this example, so in this way, we are getting the following picture. So classification result at dimension D plus 1. So let's consider this as some group, right? So this is the answer we are getting to. And there is a map. So by considering JT, you get this type of homomorphisms. Mathematically, this is given by hom from omega S D plus 2 to Z. So this JT gives this information. So now we need to understand the kernel. So what's the remainder? So the classification result at dimension D plus 1. So let's say you take a gapped phase here, and suppose JT is 0. Suppose JT is 0, so that this part is 0. What happens is that IT of MD itself, if MD is a boundary, sorry, plus 1, of 2-dimensional manifold, this is supposed to be integral of JT and then D plus 2, right? But this is 0. In other words, if you have 2 MD plus 1, which are bordant, the difference of the value is 0, mod 1. This means that IT itself, when JT is 0, gives a map from the same Bourdism group, but with dimension D plus 1 to R over Z. Now, suppose omega S D plus 1 is something like Z to K plus some torsion part, right? Then what are such functions? What are such functions? Such functions are hom from ZK plus, well, let me just have one factor, R over Z, right? But the homomorphism from Z to R over Z is just R over Z, right? You just have to specify the image of the generator. You have K copies of that. And for each Zn, you need to specify the image of 1 mod n. And that's the nth root of unity. So you get like something like this. But the important point is that this part is discrete, but this part is continuous. And we are classifying phases up to continuous deformation. And this part is continuous, so you need to drop them. So in this case, because of that, this question mark part corresponds to home of the torsion part of omega d plus 1 s to R over Z. So this gives the final answer to the classification result of d plus 1 dimensional gapped phase with structure S. So that is a certain extension of home from omega d plus 2s to Z by the torsion part to R over Z. That's a complicated result, but not so complicated after all, because you see, so the object we are getting is just omega d plus 2s and omega d plus 1s, right? Let's say this is z to k plus zni, and this is z to l plus I zmi, right? So for this part, the only way to send zn to z is to 0, because n times the generator is 0, but n times 1 is necessarily non-zero, so this part is gone. So this is just zk. So if you know this group, all you have to do to compute this home is just to throw away the torsion part. In order to get this, first we need to get the torsion part. So instead, you throw away this non-torsion part. And the home from this torsion group to R over Z is at the level of the abstract group. It's just the torsion part. Mi. And you have an extension of non-torsion group with torsion group. And there's no non-trivial way to do this. So this just becomes zk plus zmi. So at the mechanical level of getting this classification result, all you have to do is to take the non-torsion part from here and the torsion part from there. So that can be very easily done by looking at this. So let me really finish. Yeah, sorry, I said I will finish by 15, but 20. But let's just have a look at this, right? So what would be the So let's say you want to consider spin Mordism groups. In the spin case, then what do you want? So let's say 1 plus 1d, 2 plus 1d, 3 plus 1d, ... right? So here you have 1 plus 1d, right? So then here you have 1 plus 2, which is 3, which is 0. And here 1 plus 1d has 1 plus 1d. So I look at this entry, z2. And you just take the torsion part. So this is z2. So this is just z2. In the 2 plus 1d case, you look up the d equals 4 line. So this is z. So this is z. And here you have 0. So you have 0. So this is you get z. And similarly, if you go to consider z plus 1 case, this gives you 0. And this is z2, and you get z2. So this is the result of the classification for the spin case. And you can do the same thing with spin minus. So as before, you can consider 0 plus 2 dimensions, and 1 plus 1, and 2 plus 1. For example, let's consider 1 plus 1 case. So in this case, you have a look at the entry 3 here, which is 0. So this is 0. And here you look at the entry 1 plus 1, which is z8. So this becomes z8. So this becomes z8. And things like that. Here you get z2 and 0, and you get z2, and so on and so on. So this is exactly, so this z we already know, right? This is the quantized thermal Hall coefficient. So this z, that quantized thermal coefficient, Hall coefficient, distinguishes 2 plus 1 dimensional spin fermionic gapped phases. And in the p minus case, which means that t squared equals plus 1, in 1 plus 1 dimensional fermionic case, it has a Z8 classification. So that's generated by the Kitaev chain in the non-trivial phase, and so on and so on. So that's the final result I presented. And the next week, I would like to put this in context of generalized homology theory. Yeah, so sorry for going over time, but in any case, this lecture series is going over time from the regular set of lectures. So next week is really the final lecture in this series, and I'm going to wrap up by putting this into a mathematical context. Thank you very much. More questions? I think we can switch to Japanese, I guess. はい。どうぞ。はいはい。はいはい、これ。オメガ3。はい。はい。オメガ2、オメガ1とかなんか。はい。はい。ですね、それは非常にいい質問でして、一般論として、アンオリエンテッドボルディズムグルンの場合は、これ、アンオリ。これ、D っていうのは、これは必ず、スティーフェルフィットにいる WNI、WN1、WN2、WNK で、ただし NI の和が D になるやつを適切にその多様 MD で評価して、それの01を調べると区別できるっていう定理があります。1個だけじゃなくて全種類考える。全種類考える。だから その Z ファクターの場合は、Z ファクターの場合はディファレンシャルフォームで作れるやつを全部考えたのと1対1に対応するっていう定理がありましたけれども、アンオリエンテッドの場合は、これをいろいろ考えればいいんですね。そうすると5次元の場合だと D が5だと W1 の5乗と、W2、W1、3乗とかジャジャジャジャっていっぱいあるんですけど、また別の一般論として特定のポリノミアルはいつでも0になるっていう結果があるんですよ。例えばアンオリエンテッドマニフォールドでもM1 乗で W1 を積分すると0っていうアホな結果があるんですね。これは何でかっていうと、そのアンオリエンタブルマニフォールド考えてもいいよって言っても S1 しかないので全部オリエンテッドなんですよ。だから W1 積分したら0になっちゃうというアホみたいな話があるんですね。でそういう例がトリビアルにあるんですけど、あとその2次元の時は W1 足す W1 の事乗足す W2 っていうのを積分するとこれも0になっちゃうことが知られててそういうなぜかその多様体だっていうだけでですねこれはボルディズム考える際に大切なんですけど、多様体 M っていうのがあってこの上に勝手なON バンドル考えますね。そうするとこれからステイフェルフィットのリール以外 WI とかあるわけで、そうすると勝手なON バンドル考えるとこれがノンゼロになるような ON バンドルって絶対作れるんです。それは一般論として十分に複雑なベース多様体を考えて十分に複雑なON バンドル考えると絶対どんなキャラクタリスティッククラスでもノンゼロにできるっていうのはそういうもんなんですけど、よく考えると。でも多様体自体を考えるときは勝手な ON バンドル考えられなくってタンジェントバンドルしか考えられないんですね。タンジェントバンドルで評価すると0になっちゃうとかいう不思議な結果がいっぱいあるんです。でこれが一番簡単なケースなんですけど、そうすると数学の本を読むとZ 上でその W1、W2、W3 点々点で生成されるなんか勝手なスティーフェルフィットニー類の多項式いっぱい考えられるんですけど、その中でどうしても多様体のタンジェントバンドルを考えているせいで0になっちゃうっていうイデアルがあって、それで割ってやったものとこれが一致するっていうことが知られています。はい。でここの場合は W2、W3 で決まっちゃうよっていうそういう性質があります。はい。確かこれと W5 が一緒になっちゃうんだったと思いますけど、まあ、なんかあるんです。はい。他に質問はどうぞどうぞ。そうです。リラティビスティックな。はい。
今のそのボルディズム群の表を見ながら、その表ってあれですか、レクチャーノート
貼ってるやつです。はい。はい。このずらす作業をして組み直したやつのレクチャーノートにも書いてますけど、いやインタラクティングの全部それインタラクティングのやつです。
だからこのあれですか、アンダーソンデュアルって書いてあるやつがそれ。
はい、最新のやつはこれ。だから今時間なかったですけど、このだからややこしい結果ですよね。こっち側にホムなんとか Z があって、でこっち側になんかそのホムトーション、だからここが D 足す1なんだけど、ここが D 足す2で Z になってて、ここが D 足す1でさらにトーション取って R オーバー Z 取るとかで、なんでこんな意味不明な組み合わせするんだっていうことになるんですけども、これは実はアルジェブライクトポロジーでは標準的な操作でここに出てくるものがあって、これのことをアンダーソンデュアルとか言うんですけど、表では載せてるので D 足す2とか書いてる。はい、そういうやつになってる。だから基本的にはトーションパートは1個下げるんですね。ノントーションパートの場所は置いといて、トーションパートをガポッと1個下げればいいので、ルールとしては。だからこれ持ってたら別にすぐ普通にトーションパートの方が少ない、ノントーションパートの方が少ないからそっちずらした方が簡単なんですけど、ここを Z にしてと、ここが Z かな。 ここが Z、ここが Z でしょ。で、Z を1個上に動かせばいいので、ここはここにくっつきちゃうんですね。それで、ここだけ Z2 をここに動かして、ここだけ Z に動かして、でここは Z。でここも Z。でこれは全部動かさないといけないからですけど。まあ、こんな感じで。メカニカル。
あんまり、
はい。
レファレンスとかはなかったんですけど、これを最初に言ったのが、
あ、すみません。レファレンス行くまで、すみません。ノートができてませんが、これは最初に言ったのは、この表、そうかで。
当時、なんか、まあ、てか、例えば記録したりとか、二流するみたいな議論が、
そうそうそうそうそう。
だと、なんだろう、もうちょっと、例えば、カバースター
そうそうそうそうそう。いっぱいあります、いっぱいあります。だからこうやって、だからまあ、だからフィドコフスキー気体譜がとかでいろいろそのリダクションあるねっていうのをやって、で同時にその偶弁とかがこの低い辺、そのスピンのこの低い辺はスーパーコホモロジーで書けるとかいうことをやってて、この辺が両方だったんだけども、その後まあ、ヘプ TH の人のカプースティン、ソーングレン、トゥルツィロ1っていう論文で、トーションパートに関しては、オメガスピンのトーションパート、ここをアイデンティファイしたんですね。論文があって、その後にフリード&ホプキンスっていう数学の代数トポロジーの人まで伝わって、この人たちがフォーミュレートしたのはこのルールです。だからコンドマットのがヘプ TH の人に取り上げられて、それがさらにマス .ag、だからコンドマットからスタートして、コンドマットストア L のが奪われるというか、ヘプ TH に行って、マス .at か、AT まで行ったという面白い話でして、ここからここに直接行くにはちょっと翻訳が大変だったんですけど、一旦ここで1ステップ組むとここまで行って、でこうやってフォーミュレートされたという話になってます。でもここにいる気体譜がそもそもこの辺で一般コホモロジー理論で書けるとかいうのはすでに言ってたので、ただどの一般コホモロジー理論かっていうのは気体譜よく知ってますよね。どうなってるんですかねとか思うんですけど、という流れです。はい。あと、それフリード・ホプキンスっていうと、米倉君に悪いんで、米倉君もやってる、並列してやってたと思います。はい、米倉。はい、はい。米倉君もやってたので、はい。今、東北大の。ちょっと違う問題考えてたんですけどね。カプースティン・ソーングレンの正当化の方法として、フリード・ホプキンスっていう方法と米倉っていう方法とあって、違う問題を考えてて、カプースチンじゃないや、フリード・ホプキンスはギャップとフェーズで JT があってもいいんだけれども、アップトゥコンティニアスデフォーメーションで分類するっていうとフリード・ホプキンスなんですね。米倉君のやつは JT を0の場合だけ考えるんだけど、アップトゥコンティニアスじゃなくて、もうこれ自体を考えるということをする。だからそうするとさっきこの JT が0だったら JT が0だったらその IT っていうのはホムの IT っていうのはオメガ S の D プラス1からR オーバー Z へのホム全体になるって言ったんだけども、さっきはこれが ZK プラストーションだったらこのホムの空間っていうのは R オーバー Z の形状足すここのトーションになるんだけど、ここは連続的に変形できるから落とすとかいうことをしたんですけど、そこをしないでこれだけを気にするということももちろんできるんで、そういう問題を考えてもいいんですけど、そういう問題考えると、米倉君の論文を読んでいただいた方が分かりやすい。フリード・ホプキンスはJT がノンゼロの場合を考えないといけないせいで数学的にむちゃくちゃ難しくなります。はい。でも JT が0だったら トポロジカルフィールドセオリーになるんですよ。だから、その MD のトポロジーにしかよらないので、ND 足す1で JT を積分したやつがあるとかいうと、連続変形で場の理論が値変わるんですね。でもそうすると、そのトポロジカルじゃないんで、いやまあ、クオンタイズドホールエフェクトとかあるってことは、なんか多少ダイナミクスが起こってるってことなんですけど、ちょっと難しい。でもこっちにしとくと、これを JT0 にしとくとかなり簡単になって、ですから米倉君のこの論文は非常に読みやすい。非常に丁寧に書いてあって、非常に分かりやすいので、まあ、これも、すいません、リファレンス突っ込む暇がなくて、いずれレクチャーノート、はい。そうです、そうです。10日というのは、
最後に得られる。
いや、最後に得られる結果は違います。だから、JT、アノマリポリノミアルというか、だから、クオンタイズドホールコエフィシエントとか全部ゼロなんだけれども、そういう理論をアップトゥコンティニュアスデフォーメーションじゃなくて、ここも含めて分類するとどうなりますかっていう問題考えると、それは米倉君の結果になるし、JT は許すけど、アップトゥコンティニュアスデフォーメーションとかいうのもある。で、両方考えるというバージョンもあるんです、もちろん。両方考えてもよくて、それは米倉山下っていう論文があって、山下の著名な山下真由子さんですけれども、それはなんかディファレンシャルアンダーソンデュアルとか言ってさらに難しい代数トポロジーのものになるんですけど、でもあってちゃんと数学的にもフォーミュレーションされているので、それも示されてる。だからその辺は、だからレラティビスティックな場合は非常に整備進んでいるので、はい。はい。はい。いや、だからですね、だから最終的には米倉山下を使うのが一番正しいというか広くて、フリード・ホプキンスも米倉君の元の論文もそれの一部分になってるという感じになってます。はい。でもそれぞれ微妙に何をクラシファイしているかっていうのは違うので、だから問題によって答えは変わってきます。はい。はい。そうそうそうそう。そうそうそう。
それは SPT の分類とは違う問題になる。
それは SPT の分類の一種なんですけど、どういうタイプの SPT を分類するかということで、だから SPT なんだけど、クオンタイズドホールコンダクタンスとかは全部ゼロですよと言った上で、コンティニュアスデフォーメーションを気にせずに、もう含めて分類するというのをやると米倉君なんです。だから SPT を分類するっていう言葉だけだと、ちょっと曖昧さが残って、どの程度のクラスの SPT を考えて、さらにどれぐらいその詳細に分類するかとかいうのをいろいろ変えられるので、それによって答えが微妙に変わってくるのは、まあそれは仕方がないことなんですけど、はい。はい。そうです、そうです。
それはトポグラフィーのセオリーじゃない。なんかどういう意味のトポグラフィーのセオリーっていう。
そこもまた非常にテクニカルな話で恐縮なんですけど、ですね、普通物理屋さんはチャーン・サイモンズ理論はトポロジカル場の理論だって言うんですけど、数学者に言わせるとチャーン・サイモンズ理論はトポロジカル場の理論にするにはフレーミングっていうのを入れないといけないんですよ。通常の意味の物理屋が言ってるチャーン・サイモンズ理論っていうのはだから数学者はアホなのでですねアホというか定義に忠実なので定義を牧取するので TQFT って言ったらトポロジーにしか呼ばないんだぜっていうわけです。だから2たす1次元だったらスペーシャルスライスは M2 でその N3 あって、それでパーティションファンクションとかはトポロジーにだけ寄ってくださいっていうわけなんですけど、でもパーティションファンクションが AF だったりするじゃないですか。これはトポロジーだけじゃなくて、その上のパヨタの上にバンドルを与えて連続的に依存するじゃないですか。だからそれはトポロジカルじゃないですよねっていうレベルの話があって、だから本当にダイナミカルなむちゃくちゃ難しい QFT と本当に TQFT の間にここに微妙なところがあるわけです。その クオンタイズドホールコンダクタンスぐらいを許すとかいう微妙なところがあって、でここを人は何て言うか知らないんですけど、正しいやつは。だからフリード・ホプキンスがクラシファイしてるのはこの辺なの。で、米倉君がクラシファイしてるのはこの辺なわけ。で、そこの微妙な違いっていうのは物理屋には普通分かんないんですよ。物理はこっから下は全部、お前らそんなもん TQFT だろうというわけなんですけど。フレーミングが必要っていうのはまたこれもややこしい話でございましてですね。いや、全然僕今日皆さんいくらでもこういうオタクな話をするために集まっていただいてるんだと思うので。ですね、ですね、ウィッテン先生のチャン・サイモンズ理論の元の論文を読むと、すでに書いてあるんですけど、はい。そうです、そうです。ですね、エクスポネンシャルの、だから経路積分ってだから DA ってして、で、そのトレース ADA 足す AAA とかするわけでしょ。K 倍の。これってやると、その大体これのことを ZM3 ってすると、この場合はその M3 って多様体にメトリックあるだけなんですね。メトリックあるだけで、ここのゲージ場の方は積分しちゃうから、で、さらにここにそのメトリック現れないじゃないですか。だからこれって TQFT、ここでいうところの、ここの TQFT になりそうな気がするわけです。でも、もともとのウィッテン先生の論文にすでに書いてあるんですけど、これっていくらアホなそのメトリックに依存しないような気がしても、その経路積分しないといけないんですね。そうするとこれって無限次元の経路積分がいるので、レギュラリゼーションとかいらないといけなくて、そこでメトリックディペンデンスが実は入ってくるんですよ。で、ここ微妙にメトリックディペンデンス入るんです。そのことを元のジョーンズポリノミアルの最初の論文の前半はひたすらそこのこと書いてあるんですよ。びっくりするんですけど。で、僕そこ最近まで全然何やってるのか分かってなかったんですけど、彼が言ってるのは、ここのメトリックディペンデンスっていうのは、これのレギュラリゼーションから来るメトリックディペンデンスっていうのは、そのオメガ D オメガ足すオメガ3乗っていうグラビテーショナルチャン・サイモンズのなんとか倍っていうのに比例してるってことをすでに元の論文で言ってるんです。だからびっくりなんですけど、ジョーンズ・ポリノミアルの論文でそう言ってて、だから普通に定義したやつは実はここのレベルの TQFT なの、微妙な。なんですけど、数学者はそれ嫌いなんですね、こんな連続的不変の。で、これをどうやって消すかっていうと、その手でこれ引き去るんです。手で引き去っておいたら、そりゃメトリックによらなくなりますよね。でもその手で引き去る際に、オメガっていうのはそのゲージ場だからユニークな定義ないんですね。だからオメガっていうのをユニークに定義するにはどうするかっていうと、3次元多様体って3次元多様体の特殊情報なんですけど、フレームっていうのは取れます。フレームっていうのは3次元多様体の各点上で座標系を本当に X の123って決めちゃうっていうことをグローバルに取れるんです。でそれを1個フィックスします。いいですか？1個手で与えるんですよ。そうするとオメガっていうのがそれにレラティブに定義できるので、それを通って引き去っておくことができます。そうすると、本当にそれってトポロジーにしかよらなくなるんですけど、その時のトポロジーっていうのは M3 だけじゃなくって単なるこれってスピン構造よりもっと強くて、各タンジェントバンドルの各点ごとにフレームを固定しなさいっていうので、これってフレームドマニフォールドっていうやつになるんです。だからここがオメガ D のフレームドっていうやつに対応するやつなんです。そこまで最初のジョーンズ・ポリノミアルの論文に書いてあるんですけど、おかしい、絶対未来から来たとしか思えないんだけどそこまで書いてあるんですけど、そうするとフレーミング入れたらTQFT になるんです。というのも実はまだ嘘ででもフレーミング入れとけばいいのかな。フレーミング入れてフレーミング入れたらいいのか。
レギュラリゼーションの結果出てくるものを最初から
そうそうなんですけど、だからそのウィッテンのジョーンズ・ポリノミアルの論文があるじゃないですか。チャン・サイモンズあれが80年代後半でしょ。それを数学者が TQFT としてちゃんとフォーミュレートするまでに時間があって、 そこはこのフレーミングを入れるっていうところをどうちゃんと扱うかっていうのはものすごい大変で、だからこの初期の90年代初期の数学の TQFT の論文を読むと、ひたすらフレーム付きの多様体とは何かとか、フレームのついてる多様体のボルディズムとは何かとかいうのが、ものすごいページが費やされるんですけど、でそこ大変なんですけど、でも最終的にフレームっていうのはでもここを引き去るっていうのはその数学的な消えちゃったけど本当は消えてないよ、ここの TKFT に落とし込むために人為的に入れてるやつで一般にはできないんですよ。3次元だから3次元もそれもオリエンテッドだからフレームあるんですけど、3次元でアンオリエンテッドだったりするとフレームないので、だから3次元のピンマイナスの TQFT とか考えようとするとフレーム取れないからここの議論できないとかですね、いろいろ問題があるんですね。米倉君のすごいのはそれをずっと分かってて僕この話10年ぐらい前に始めて米倉さんと一緒に始めたんですけど、当時僕ここの違いが分かってなかった。引き去る前のこれと引き去った後のこれと、だから僕、いや、あんなもんチャン・サイモンズ理論 TKFT だよねとかって米倉君が違いますと。いや、でもこれ引き去ったらTKFT になってるじゃん、1.先生もそう言ってるじゃんって言うと、いや、あれを引き去るのは非物理的なことをやってるんで信じてダメですとか。彼は正しかった。この件についてだからまあ一番偉いのはウィッテン先生かもしれないけど、次に偉いのは米倉君かなと思っている今日この頃でございます。はい。その他ご質問は？聞いていいです。いや僕全然今日は大丈夫なんですけど。はい。はい。
マッシブフェルミオンの
はいはいはい。どっかで切り替わってて、それはその僕のモチベ、嘘。エータインバレントはベリーマッシブフェルミオンのパーティションファンクションだったんですけど、そう、これを、そうです。そこでジャンプがあったわけです。これですね。これをどこまで信じるかということなわけです。
インターインバリアントの時は、要はベリーマッシュフェルミオンでそうの式が成り立って育ったことを納得するためにこの間。そう。突然これ成り立ちますよねとか言っても何も分かるかって気がするわけなんですけど、その APS インデックスエレメント数学的に成り立っているので、ベリーマッシュフェルミオンの時はこれは成り立っているわけです。はい。だからもっと一般的なエペシス定理みたいなものがあればそれが成立することが言える。
そうです。でもそのためにはこっちをこの関係式と別にそのフェルミオニックギャップとフェーズというのを数学的に定義できたり、そこからこの性質が導出できたらいいんですけど。
でもその IT っていうのは今さっきこのアンダーソンであるところを使って定義したこと
でもないんですよ。だから山下米倉ではどうやってるかっていうと、これからスタートして全部やるとディファレンシャルアンダーソンデュアルっていうこれからスタートして自然ななんかディファレンシャルジェネラルとホモロジーセオリーっていうのを作れるんですけど、それがディファレンシャルアンダーソンデュアルになっているってことが示したっていう論文。
人はなんか IT を全然違うところから
そうしていきたいわけです。
存在するよみたいなことが示せると
いいんです。それはまだできてない。それはフリード・ホプキンスもやってないんですよ。フリード・ホプキンスもだから大体なんかインタラクティングなインバーチブルフェーズってこういうもんなはずだよねとか言ってて。
でもなんていうか経験上この分類がうまくいってるんだろう。
そうです。信念ではあります。ただできてるわけではない。だから数学的にできてるのはむしろこっからスタートするとディファレンシャルアンダーソンデュアルだからディファレンシャルアンダーソンデュアルオブボルティズムグループっていうのは全然別個に純粋にアルジェブライクトポロジーで定義できるものなんですけれども、それのモデルの一つにこれがなっているっていうのを示したのが山下米倉の数学の論文になっているので、でもそれはだからスターティングポイントですね。これやっちゃうんです。入れちゃうので、だから物理的にはまあ信じていいのかなとか言って、でも言ってることはそのスモールバリエーションはチャン・サイモン図項ですよって言って以上のことは言ってないんですけど。どうぞ。じゃあまだこっちは質問していくんです。 はい。A、A、A、A、A、A、A、A、A、A、A、定義はできます。はい。A できます、できます。A、A。別に定義はできますが、計算は大変でして、A、A、A、A、だから Z のファクター、当初じゃなくてノン当初のところについては、それでいいんです。はい。だからトレース R、ウェッジ R とか、トレース F ウェッジ、F ウェッジ F とか、そういうのだけで OK っていうのは証明されてますので、だから Z ファクターがいくつあるかっていうのはそれだけで済みます。はい、そこは、本当、アルゴリズム的にはできなくて、アートなので、でそれをある程度話そうというのは次回前半は一般論をやってで具体例の計算どうやるのかという話をやってで最終的にはそういうのができる計算できると知り合いに頼むというのが多分正しい方法でございまして。ですね、計算手法だから来週話しますけど計算手法に大きく2つあって、来週ですね。そうそうそう。そんな、そんな。まあでも最終的には人に聞くと。それに関して非常に、ね、来週も話しますけど、いいウェブサイトがあったんですけど、マニフォールドアトラスって言って、その数学者が作ってるウィキペディアみたいなやつでものすごいハイクオリティな多様体に関するコメントがいっぱいあったんですけど、去年の12月ぐらいになんかオフラインになっちゃって、すごい困った。っていうのに、今週の講義用途を作ってて気がつきました。この表って全部マニフォルドアトラスにあるんですけど、それぞれ。でも、ウェブサイトがなくなってしまっているなんて、みたいなので、ちょっと、いや、マックス・プランクの人がやってたから、そうだ、これ、13時からですか？これは大変だ。